Download this code from codegive.com, link in the description below. OK, let's dive into the cargo loading problem using dynamic programming. This will be a comprehensive guide with detailed explanations and a code example in Python. 1. Problem definition: the cargo loading problem. Imagine you have a cargo ship with a limited weight capacity, W. You are presented with a set of items, each having a weight, W_I, and a value, V_I. Your goal is to select a combination of items to load onto the ship that maximizes the total value of the cargo without exceeding the ship's weight capacity. Formally asterisk. Asterisk input asterisk. Asterisk n, the number of items. Asterisk w, the maximum weight capacity of the ship. Asterisk weights equals W_1, W_2, W_n, a list of the weights of each item. Asterisk values equals V_1, V_2, V_n, a list of the values of each item. Asterisk output asterisk the maximum total value of items that can be loaded onto the ship without exceeding the weight capacity W. 2. Why dynamic programming? The cargo loading problem, also sometimes called the knapsack problem, but with a focus on maximizing value instead of merely fitting items, is a classic optimization problem. A naive approach, like trying every possible combination of items, would have exponential time complexity, O2 sup n/sup, making it infeasible for large numbers of items. Dynamic programming provides a significantly more efficient solution. The core idea behind DP is to break down the problem into smaller, overlapping subproblems, solve each subproblem only once, and store the results in a table, or memoization structure, to avoid redundant computations. 3. Dynamic programming approach: the table. We'll use a 2D table, matrix, to store the solutions to our subproblems. Let's call this table DP. Asterisk DPIW represents the maximum value that can be obtained using the first I items 0 to I1, with a maximum weight capacity of W. 4. Defining the recurrence relation. The heart of dynamic programming is the recurrence relation. This defines how to calculate the solution to a larger subproblem based on the solutions to smaller subproblems. For each item I, from 0 to n1, we have two choices. 1. Include the item I asterisk if the weight of item I, weights I, is less than or equal to the current weight capacity W, we can include it. The maximum value in this case would be the value of item I, values I, plus the maximum value we can obtain using the remaining items, 0 to I1, with the remaining weight capacity, W, weights I. This is expressed as values I plus dp I1 W, weights I. To exclude the item I asterisk if we don't include item I, the maximum value is simply the maximum value we can obtain using the first I1 items with the same weight capacity W. This is dp I1 W. Therefore, the recurrence relation is 5. Base cases: initialization. We need to initialize the first row and column of the DP table. Asterisk first row, I equals 0 dp 0 W represents the maximum value we can obtain using no items. Therefore, dp 0 W equals 0 for all W. Asterisk first column, W equals 0 dp I0 represents the maximum value we can obtain with a weight capacity of 0. Therefore, dp I0 equals 0 for all I. 6. Algorithm. 1. Create a DP table of size, n plus 1, x, w plus 1, where n is the number of items and w is the maximum weight capacity. 2. Initialize the first row and first column of the DP table to 0. 3. Iterate through the DP table, row by row, from I equals 1 to n, and column by column, from W equals 1 to W. Asterisk for each cell dpiw, calculate the maximum value using the recurrence relation. For the final result, the maximum value that can be obtained, will be stored in dp and W. 7. Code example, Python. 8. Explanation of the code. 1. Cargo underscore loading, weights, values, capacity, asterisk. This function takes the list of weights, the list of values, and the capacity as input. 2. N equals len, weights, asterisk gets the number of items. 3. dp equals 0 for W in range, capacity plus 1, for I in range, n plus 1, asterisk creates the DP table, initialized with zeros. Note the plus 1 in both dimensions to account for the base cases, 0 items or 0 capacity. 4. Nested loops asterisk the outer loop, for I in range, 1, n plus 1, iterates through each item, from 1 to n because I equals 0 is the base case. The inner loop, for W in range, 1, capacity plus 1, iterates through each possible weight capacity, from 1 to capacity. 5. If weights I1 equals W asterisk this checks if the current item, I1 because the indexing is 0 based in the weights list, can fit within the current weight capacity W. 6. dpiw equals max, dpi1w, values I1 plus dpi1w, weights I1, asterisk this is the core of the dynamic programming solution. It implements the recurrence relation. We take the maximum of asterisk dpi1w, the value obtained without including the current item. Asterisk values I1 plus dpi1w, weights I1, the value obtained by including the current item, its value plus the maximum value achievable with the remaining items and the remaining capacity. 7. Else, dpiw equals dpi1w asterisk if the current item's weight exceeds the current capacity, we simply inherit the value from the previous row, i.e., we don't include the item. 8. Return dp and capacity asterisk after filling the entire table, the solution, the maximum possible value, is stored in the bottom right cell dp and capacity. 9. Time and space complexity. Asterisk time complexity asterisk O, n asterisk W, where n is the number of items and W is the maximum weight capacity. This is because we fill each cell in the DP table once. Asterisk space complexity asterisk O, n asterisk W, because we store the DP table. In some variations, you can reduce the space complexity to O, W, by using only one row of the DP table, since you only need the values from the previous row to calculate the current row. However, this optimization makes it difficult to reconstruct which items were included in the optimal solution. 10. Reconstructing the solution, finding the selected items. The code above only calculates the maximum value. If you also need to know which items were selected to achieve that maximum value, you can trace back through the DP table. Here's how to modify the code to reconstruct the solution. Explanation of the reconstruction asterisk. 1. Selected underscore items equals asterisk initializes an empty list to store the indices of the selected items. 2. W equals capacity asterisk starts with the full capacity. 3. For I in range, n, 0, minus 1 asterisk iterates backward through the items, from n down to 1. 4. If dpiw equals dpi1w colon asterisk this is the crucial part. If the value in the current cell dpiw is different from the value in the cell above it dpi1w, it means that the current item, I1, must have been included. Why? Because if it wasn't included, the value would be the same as the cell above it. 5 selected underscore items. Append, I1, asterisk if the item was included, add its index to the selected underscore items list. 6 W dash equals weights I1 asterisk update the remaining capacity by subtracting the weight of the included item. 7 The selected underscore items list will contain the indices of the items that were part of the optimal solution, in reverse order. You might want to reverse the list if you need them in the original order. 11. Variations and extensions. Asterisk 0/1 knapsack versus unbounded knapsack asterisk the cargo loading problem, 0/1 knapsack, assumes you can only take each item once, 0 or 1 times. The unbounded knapsack problem allows you to take multiple copies of each item. The dynamic programming solution for the unbounded knapsack is slightly different. Asterisk fractional knapsack asterisk the fractional knapsack problem allows you to take fractions of items. This can be solved using a greedy algorithm, sort items by value/weight ratio and take as much as you can of the most valuable items. Asterisk multidimensional knapsack asterisk you might have multiple constraints, example weight, volume, etc. This increases the dimensionality of the DP table. 12. Conclusion. Dynamic programming is a powerful technique for solving optimization problems that can be broken down into overlapping subproblems. The cargo loading problem is a classic example. Understanding the recurrence relation, base cases, and how to reconstruct the solution are key to mastering dynamic programming. This detailed tutorial should provide a solid foundation for tackling similar optimization challenges. Good luck.